I'm going to talk about voltage, resistance, and Ohm's law. I would recommend you watch the introductory video on electric circuits before this one. Okay? Now I'm going to talk about voltage. Voltage is used to determine the electric potential energy differences of charged objects between points. As charged objects move along electric circuits, okay, you might wonder how their electric potential energy is changing. Okay, so voltage differences between 2 points can be used to determine electric potential energy differences. So you say, well, how is voltage related to electric potential energy? All right, the product of charge and voltage is equal to the electric potential energy. All right. So for a specific amount of charge, for a specific charged object, the voltage and the electric potential energy are proportional. Okay, if one gets bigger, the other one gets bigger. Now, I've referred to voltage to denote a difference between 2 points, and I've also talked about the value at each point. All right. Now, most often we will be concerned with the change in the value between 2 points. Okay. The value at a point is not so important as it is compared to neighboring points. All right. Likewise, with respect to electric potential energy, often we're more concerned about the change. All right. Now, the units of voltage are volts. That's denoted with a capital V. It can possibly be confusing if someone uses the letter V to denote a voltage value, because the letter V is also used to denote volts. Okay, so just keep that in mind. Now, voltage corresponds to pressure. That last sentence is just an analogy. It's meant to provide an image. All right, let me show you what I mean. So I'm going to make a picture of a battery. And you may know that those little knobs on the top of, let's say, a car battery are referred to as nodes. And you might have noticed that there is one of them is labeled with a plus and one of them is labeled with a minus. All right. Car batteries are typically 12 volts. All right, let's talk about what all that means. So, suppose that we hooked up a wire between the nodes of this car battery. And suppose that electrons moved from the negative node to the positive node. All right, then as they moved from one node to the other, the change in electric potential energy would equal the product of the charge of the electron and the difference in the voltage at each node. So 12 volts denotes the difference. So we might say that the negative node is at a value of 0 volts, and we might say that the positive node is at a value of plus 12 volts. Okay, the difference is what has to be 12 volts. Okay, so you multiply those values by the charge of an electron and you can find the change in potential energy. Okay, now what did I mean when I said that voltage is like pressure? So when I think of a high electric potential energy, okay, in other words, when I think of a high voltage with a positive charged object, or likewise a negative voltage with a negative charged object, I think of a high pressure area. For example, think about the air inside of an inflated balloon. All right, the air is just it's like it's dying to get out. Right, if you puncture the balloon, the air inside the balloon rushes out. Okay, now think about a vacuum. That's a low pressure. It wants to suck air in. So all that is to say that when you think about electrons moving between the nodes of this battery along the wire, think of the electrons rushing out of a high pressure area, like rushing out of a balloon into a vacuum. Okay, so that differences in voltage values are like differences in pressure. Okay, if that's a useful analogy or useful image, go ahead and use it. If not, don't worry about it. All right. Now I'd like to talk about resistance. So we've discussed voltage. We've discussed how it leads to differences in electric potential energy and likewise electric forces, which lead to currents. All right. Now, currents can more easily flow down certain materials compared to other materials. All right. Resistance describes a material's, its resistance to electric current in response to a voltage. So let's say you had a super high voltage battery and you wanted to create some current, a lot of current through some material like a wire, okay? Well, the resistance will determine how much current you actually get. You can do internet searches for the resistance values of different materials. Copper has a very low resistance. That's why we build wires out of copper, because we can get lots of current through copper. All right? On the other hand, wood or glass don't have a much larger resistance. Plastic has a very large resistance. That means you are going to get very little, if not zero, current through those materials. Okay? Resistance has to do with resistance to current. The units of resistance are ohms, all right, named after Mr. Ohm, a scientist that studied electricity, studied currents. All right? And resistance is denoted by, the resistance is often represented by the variable R, just like voltage is often represented by the variable V. All right. So now I'd like to discuss how the voltage changes as you move through a material of a given resistance, okay? And how that's related to the current. So suppose I had a section of wire. Give me a minute to make a picture. And let's say that the resistance of this material was some number of ohms, so I'll denote it by R. And let's say that the voltage difference between the ends of that piece of metal, that piece of wire, was some number of volts. We'll denote that by V. All right. Now, how is that related to the current that I will get in the wire? So, and by the way, current is traditionally denoted by the variable I, not the variable C, which you might guess for current. Okay, so you'll see me use I often for current. So the current, the more voltage that you have, the more current you're gonna have. So it's actually proportional to the amount of current. So I'm going to say current is equal to some coefficient times the voltage. Okay. Now, and that coefficient is related to the resistance. Now, the resistance, more resistance is going to mean less current. So it'll turn out that you want to multiply the voltage by the reciprocal of R, or divide the voltage by R. Okay? This is what's referred to as Ohm's law. This is a very important formula. I can't emphasize enough how important this formula is for electric circuits. Okay? This relates three very important values: the current, the voltage, and the resistance. All right? Another way that this is often written is that the voltage difference across some piece of wire is the product of the current and the resistance. All right, can you see that that's the same as what I have in the box? All I did was multiply both sides by R. Okay? And then likewise, the new formula that I have, you could divide both sides by I, and you could get that the resistance is equal to the voltage divided by the current. Now, we will find reasons to use all versions that I've written there in the bottom right. Okay? Again, that is Ohm's law. Okay? Now, let me make a comment about energy and what happens with the energy values of charged objects as you move down pieces of wire with resistance. So we just said that there's a voltage difference across this piece of wire that I'm denoting in the picture, right? So that means that there's going to be a change in electric potential energy. Actually, as a charged object moves through a piece of material with the resistance, it'll actually lose electric potential energy. Okay? Why is that? Well, it takes energy to move through something that's resisting you. Okay? Through something with the resistance. Now, where does that energy go? Okay? It loses that electric potential energy to the creation of heat. The wire actually gets hotter as current moves through it. That's one place that the energy goes. Or another way to say it is that's one type of energy that the electric potential energy gets converted into. Okay. Also, the charge carriers gain kinetic energy. That's another place that another type of energy that it gets converted to. Okay. Now, think about a light bulb. A light bulb is nothing more than, if you look inside the container, there's a little wire, and that wire has a high resistance. Okay? Why does that generate light? Well, as the electrons move, or whatever the charge carriers are, as they move through that filament, as it's called, with that resistance, all this electric potential energy is getting converted to other types of energy. Okay? You're generating heat. That's why the light bulb gets hot. But also you're generating you're generating light. Okay, light has an energy associated with it. So that light is coming, that radiation is coming from the electric potential energy that was in the charge carriers before the current moved through the resistance. All right. Likewise, a toaster or an electric heater, the current, the electric potential energy of the current of the charge carriers is being converted into heat. Okay? Now I'd like to do some example problems using Ohm's law. All right, suppose that I had a 10-volt battery, and suppose that I had a resistance that was 2 ohms, and I wanted to know what was the current in that piece of wire that had 2 ohms of resistance, and there was a 10-volt, there was a voltage difference of 10 volts between the ends of the wire. Well, I would use Ohm's law to determine the current. I know that the current is equal to the voltage divided by the resistance. So 10 divided by 2, and so there's 5 amps of current in that section of wire. Okay? By the way, instead of writing ohms all the time for resistance, okay, we can't, by the way, you might think we can just use capital O, but that'll look like a 0. So electric engineers don't do that. What we can do is we can use a Greek letter to represent ohms. So I could have equivalently written the 2 ohms as 2 times capital omega, which looks like that. Okay? Now, let me have you do an example. Suppose that I had a circuit that had a current of 10 amps, and suppose the resistance of that circle was 20 ohms, and I'm going to write it using that sigma symbol for ohms. So when I said 20 ohms, that means I'm going to write 20 and then omega. Okay? Now, so what is the voltage for that circuit? The voltage difference across a piece of material that has a 20 ohm resistance. Okay, so pause the video and see if you can calculate that now if you like. Okay, I'll go ahead and work this out as well. So I is equal to V over R. So we're looking for the voltage, so I'm going to solve for V in that equation. V is equal to IR. So that's 10 times 20, which gives 200, and the units are volts, so 200, and then we'll put a capital V. Okay? Now let me have you do one more. Suppose I had an electric circuit with a 15-volt battery, and the circuit had 5 amps of current. I want you to tell me what the resistance in ohms is for that electric circuit. Okay, so pause the video and do that now, please, if you like. Okay, so I'll go ahead and work it out. So the current is the voltage divided by the resistance, or the voltage is the current times the resistance. So solving for R, I get that R is V divided by I. So 15 divided by 5 gives 3 ohms. And I'll use that omega symbol. Okay?